Hello, my name is Francis Blay, and this is my makeup for ENME 351 Lab 4. Here is my email exchange with Professor Stephen Mitchell. I had problems with my laptop earlier this semester, and so Professor Mitchell has let me take the makeup lab with the 30% deduction. Starting off, we have my circuit here with the potentiometer. If I change it, the LED should change, showing an indication of what sampling frequency that I want to sample the frequency from the ad lamp. Here is my Arduino code here. As you can see, here, if the value from the potentiometer is within certain ranges, the period of the frequency will change. For example, if the potentiometer is below around 250, then the period will be 1, and that corresponds to a frequency of, I believe, 500. This would correspond to the frequency of, I believe, 100, and here would correspond to 142, and this would be 200. No, sorry, this would be 100. This is 142. This is 200, and this is 500. Sorry. So as you can see here, if when the period of the sampling frequency is decided on by the potentiometer, it will control the rate at which the values of the signal are printed to the serial monitor to be read by processing. So after we have used the ad lamp to create the signal and use the processing code to analyze the signal in both time domain and frequency domain, we get the following results. Starting off at a sampling frequency of 500 Hertz, the first graph here is 75, here is 100, here is, 215, and this is 300. Next, at sampling frequency of 200, we have first 75, 100, 215, and 300. At a sampling frequency of 142, we have 75, 100, 215, and 300. Finally, at a sampling frequency of 100. Hold on. We have 75, 100, 215, 300. Next, to figure out our theoretical alias frequency calculations, what I did is I took the frequency, it's a sampling frequency, divided it by 2, and then took the frequency of the signal and divided that by the sampling frequency divided by 2, and then multiplied that again by the sampling frequency divided by 2. So for example, at a frequency of 75 Hertz, at a sampling frequency of 500, we get 75 Hertz for the aliasing frequency. In cases such as this here, if the frequency of the signal is 300 Hertz and the sampling frequency is 500 Hertz, we get a value of 1.2 when we divide the frequency of the signal by the sampling frequency divided by 2. This gives us 1.2, and using a floating diagram, this would correspond to 0.8 times the sampling frequency divided by 2, which is the Nyquist frequency, and this gives us 200 Hertz. So after we do this for all these sampling frequencies and signal frequency combinations, we can then put them on the table here. So this is a list of all my results. As you can see, the theoretical and experimental values for the alias frequency line up almost perfectly. Next, for exercise 2, we have the square wave, and as you can see here, we have multiple aliasing frequencies. This is due to the fact that the square wave is made up of an infinite series of sine waves acting at different multiples of the fundamental frequency. And here we have a triangle wave, which has a lot fewer aliasing frequencies. And this is due to the fact that the amplitude of the signal, the peak of the signal is held at a much shorter time compared to the square wave. this is it for my lab 4. Thank you for watching.